Discover Geography, Lesson 7-2, Climatology, Part 2. In this lesson, we're going to look at some of the basic principles that influence the distribution of precipitation levels around the world. A key concept to understand, in order to understand why precipitation occurs in certain places, is the idea of humidity. Humidity refers to the amount of water vapor present in a given portion of air. The most important way to measure humidity for our purposes is something called relative humidity. Relative humidity is the percentage of the air's total capacity to hold water moisture that is actually taken up by water vapor. Any given bubble of air is going to have a fixed capacity for how much water vapor it could possibly hold. A certain limit to how much moisture can be in that air. The relative humidity tells you what percentage of that capacity is filled. So you could have air that continues to contain the same amount of actual water vapor, but if its capacity to hold vapor changes, then the relative humidity will change. If its capacity to hold moisture increases, the relative humidity will drop because that same amount of moisture is now a smaller percentage of the total capacity that that air has. On the other hand, if that total capacity shrinks, then the relative humidity will go up because now a larger percentage of that capacity is actually being filled. If the relative humidity goes above 100%, if there's more water vapor there than the air can actually hold, then that excess water vapor will have to leave the air. It will have to form condensation. It will have to stop being water vapor and become actual small droplets of water. That condensation may stay suspended in the air for a while, but may then eventually fall as precipitation, as rain or snow or sleet or another form of precipitation onto the ground. In essence, all of our world's precipitation is occurring because something is causing the air's capacity to hold moisture to drop below what is actually in the air, and so that excess is going to come out. The main way that you can reduce air's capacity to hold moisture is to cool it off. Warm air can hold much more moisture than can cold air. So if you can get a bubble of air to cool off beyond a certain point, then you will cause condensation, which can then ultimately lead to precipitation. The main way that we typically get air to cool off is by making that air rise, by making that air go up into the atmosphere. We learned in the last lesson that temperatures get colder as you go up into the mountains. The same thing happens for air rising within the atmosphere. It gets colder as it goes up. The rate at which it cools off is something known as the lapse rate. So as a bubble of air goes up in the atmosphere, it will cool off at that lapse rate until it hits what's called the level of condensation. That's the level at which that air's capacity to hold moisture has finally decreased below the amount of moisture that's actually in it. At that point, if the air continues to rise and continues to cool off, it will start having condensation. It will essentially start forming clouds. So clouds are masses of condensation. They're masses of tiny droplets of water that have been forced out of the air as it cools off. That moisture is just hanging out in the air. Those tiny droplets of water are being suspended in the air for the time being. But of course, they may form water droplets or snowflakes that ultimately then fall out of the clouds onto the ground. Because condensation is happening as that air is rising to hit a certain point where it cools off, you often see a whole bunch of clouds with flat bottoms at about the same level. That flat bottom shows you where the level of condensation is at that particular time. That's the height at which this air that's rising at this point is cooling off enough that it has to start undergoing condensation because it can no longer hold all of the water that's in it. One of the key principles that is going to explain where this precipitation is going to occur on the Earth is something called the primary circulation. The primary circulation can be summarized by the graphic you see on your screen. The primary circulation is a pattern of high and low atmospheric pressure zones and of winds connecting them around the Earth. It's a generalization of these pressure zones and the flow of air around our Earth. Now, looking at this diagram, it may look very complex, but we can break it down into subcomponents so that you can understand everything that's going on here. So let's zoom in on the portion of the Earth between 0 degrees, the equator, and 30 degrees north. At the equator, we have a permanent zone of low pressure. At 30 degrees north, we have a permanent zone of high pressure. When we have low pressure, that means the air is ascending. It's going up into the atmosphere. You can imagine this like that air lifting up off of you. And if the air is lifting up, it's not pushing down on you as hard. So that's low pressure. At a high pressure zone, the air is descending. It's coming down. It's pushing down on you harder. So that's high pressure. When that air is going up at the low pressure zone, when that air is rising, it's going to cool off as it goes up into the atmosphere. And as it cools off, its capacity to hold moisture is going to start to decrease. And so eventually that air is going to hit that condensation level, and we're going to start to get clouds and then ultimately precipitation from that. At the high pressure zone, that air is coming down, so its capacity to hold moisture is going to keep increasing. So there's nothing to push any moisture in that air out. And so therefore, we're going to get very dry conditions at a place with high pressure. So at our equator, we have low pressure, rising air, cooling air, therefore moisture being forced out of that air and ultimately precipitation. At our high pressure zone, we're going to have descending air, warming up, more capacity to hold moisture, therefore nothing to cause precipitation. If we've got all this air rising at our low pressure zone and descending at our high pressure zone, then this sets up a sort of circular flow of air. The air will come down at our high pressure zone, it will flow across the surface of the air towards the low pressure zone, then it will rise, then it will return through the upper portions of the atmosphere back to the high pressure zone. So on the surface of the Earth, our winds are always blowing from high pressure to low pressure. And again, that should be easy to remember. High pressure, you can imagine like squeezing the air out of a balloon. It's going to blow away from that high pressure towards a low pressure area. You will need to just remember where these low and high pressure zones are located. In this lesson, we're not going to be able to explain the whole background as to why we get high and low pressure zones at certain points on the Earth. However, these shouldn't be too hard to remember because they alternate. We get a low pressure zone at the equator, then we get high pressure zones at 30 north and 30 south, then low pressure at 60 north and 60 south, and high pressure again at 90 north and 90 south, the north and south pole. So that means that we're going to tend to get lots of rain at the equator. We're going to get dry conditions at 30 north and 30 south, rain again at 60 north and 60 south, and dry conditions at the poles. And in fact, most of our major deserts in the world are located at about 30 degrees north and 30 degrees south. The Sahara, the Sonoran Desert in the southwest United States and northern Mexico, the Arabian Desert, the Kalahari Desert in Africa, the deserts of Australia, all of those are located at about either 30 degrees north or 30 degrees south, where we have this permanent high pressure zone. On the other hand, at the equator, we have a low pressure zone, lots of precipitation. That's where we have our tropical rainforests, whether it be in South America, in Africa, or in Southeast Asia. Now the wind between the high pressure and low pressure, as we said, wants to flow from high to low. So you would think that means that we have winds blowing from the north towards the south between 30 north and the equator. But these winds are affected by the Coriolis effect, just like our ocean currents are. So the Coriolis effect will bend the motion of the air to the right in the northern hemisphere, meaning that these winds get tilted to one side. So instead of being northerly winds, that is winds flowing from the north to the south, we ultimately end up with easterly winds, that is winds flowing from the east towards the west. Winds are always named for the direction they flow from. So an easterly wind goes from east towards the west. A westerly wind goes from the west towards the east. So if we apply this basic idea to the places in between all of our pressure zones, we can see that we get easterly winds between 30 north and the equator and between 30 south in the equator. In both cases, the winds are trying to flow from high pressure to low pressure, but they're going to get bent to the right in the northern hemisphere, to the left in the southern hemisphere by the Coriolis effect. And so that's going to turn out creating easterly winds in both of those zones. Between 30 and 60 degrees in both hemispheres, we're going to get westerly winds for the same reason. In the northern hemisphere, winds are trying to flow northward from the high pressure to the low pressure, but they get bent to the right by the Coriolis effect, and so they turn into westerly winds. Southern hemisphere, they're trying to flow from the high to the low. They're going to get bent to the right and become westerly winds again. This is why our major weather systems in the United States tend to flow from west to east. We can see storms coming. They may hit the west coast, California or Washington, then they move out across the Rocky Mountains, they move into the Great Plains, and then on into the eastern states, because we have these prevailing westerly winds that are the result of air trying to flow from the high pressure zone at 30 north to the low pressure zone at 60 north, but getting bent to one side by the Coriolis effect. To further complicate the primary circulation, we have the effect of seasons. The primary circulation varies with the seasons. All of the pressure and wind zones shift northward and southward with the seasons. Essentially, the primary circulation is always centered on the spot that has the most direct overhead sunlight. So that low pressure zone near the equator is actually a low pressure zone at the spot directly underneath the sun. That means that when it's summer in the southern hemisphere, winter in the northern hemisphere, that point directly under the sun is going to be somewhere to the south of the equator, as the southern hemisphere is tilted into the sun at that point in the year. And so that low pressure zone will be located somewhat to the south of the equator. And all of these other zones will shift southward in the same way. On the other hand, during the northern hemisphere summer, that point directly under the sun is going to be somewhere to the north of the equator. And so all of those zones will shift somewhat northward. If we focus back in on our zone between 30 north and the equator, the diagram that we were looking at before essentially describes the conditions during spring and autumn. So the low pressure zone is located right at the equator, the high pressure zone is located right at 30 north. However, when it's summer in the northern hemisphere, winter in the southern hemisphere, all those zones are going to shift somewhat northward. So that low pressure zone is going to be located somewhere to the north of the equator. The high pressure zone is going to be located somewhere to the north of 30 degrees. And likewise for all of the other pressure and wind zones across the Earth. When it's winter in the northern hemisphere and summer in the southern hemisphere, that whole system is going to shift somewhere to the south of where it is during spring and autumn. This means that if you are located right at the equator or right at 30 north, you're going to be pretty close to that pressure zone throughout the year. Sometimes it's going to be a little to the north of you, sometimes a little to the south of you, but it's basically going to be there year round, which means you're going to get consistent precipitation levels year round. So if you're right at 30 degrees north, you're going to get dry conditions pretty much year round. If you're right at the equator, you're going to get rainy conditions pretty much year round. However, if you are in between those areas, if you are somewhere in between 30 north and the equator, then during the northern hemisphere winter, you're going to tend to get dry conditions as that high pressure zone drops down towards you. On the other hand, you're going to tend to get wet conditions in the summer as that low pressure zone moves up closer to you. So you're going to get a situation of major seasonal differences in your precipitation. Basically, any part of the world that sees a major seasonal precipitation difference, it's due to this movement of these pressure zones over the course of the seasons. So here you see some examples of cities with these kind of seasonal wet, dry climates. If you look at the top diagram there for Hanoi, Vietnam, it's in between 30 north and the equator. And so during the summer, everything's going to move northward, and so Hanoi is going to get affected by the low pressure zone that came from the equator, and so therefore is going to get a lot of precipitation, is going to have a very wet summer. In the winter, everything's going to move southward, and so the high pressure zone is going to move southward into the vicinity of Hanoi, and so you're going to get a dry winter. So wet summer, dry winter type of situation. If you look at Darwin, Australia, that's going to have essentially the same thing going on. It's just that because it's in the southern hemisphere, its summer and winter are at different times of the year. So during December and January, Darwin is having its summer. So all of those pressure zones are moving southward towards the southern hemisphere that's having its summer. And so Darwin's going to be affected by the low pressure zone from the equator and is going to get a lot of precipitation during the winter, which in Darwin occurs in July and August. All of those pressure zones are going to move northward towards the northern hemisphere that's having its summer. And so therefore Darwin's going to be affected by the high pressure zone from 30 degrees south and is going to get a very dry winter. So Darwin and Hanoi have the same pattern of a wet summer and dry winter. It's just happening at opposite times of the year because one's in the northern hemisphere, one's in the southern hemisphere. If we then look at the city of Perth, Australia, Perth is in between 30 south and 60 south. So that means during its summer, all of those pressure zones are moving southward, which means that the high pressure zone from 30 south is going to move over Perth during the summer. So Perth is going to get a very dry summer. On the other hand, when those pressure zones all move northward during the northern hemisphere summer, which will be Perth's winter since Perth is in the southern hemisphere, then the low pressure zone from 60 degrees south is going to move closer to Perth, and Perth is going to get more precipitation. So Perth ends up with a dry summer, wet winter precipitation pattern, just the opposite of Darwin, but still with that big seasonal difference in precipitation due to lying in between those pressure zones that bring either wet or dry conditions over the course of the year. The last major thing that's going to affect precipitation levels is something called the rain shadow effect. The rain shadow effect occurs when air tries to flow over a large mountain range. So let's say we have this large mountain range and it's just downwind of a body of water. So as air flows over that body of water, it's going to pick up a lot of moisture. We can have a lot of moisture in this air. As that air flows up the mountain, it's going to cool off. It gets colder as you go up in the atmosphere, whether you're going up as a result of low pressure or you're going up as a result of trying to go over a mountain. As that air rises, its capacity to hold moisture is going to decrease. Eventually, it's going to hit the condensation level, and you're going to get condensation and then ultimately precipitation. So anywhere you have winds flowing up a mountain, you will tend to get a lot of precipitation on that side of the mountain. Now eventually, that air is going to flow over the top of the mountain and come down the other side. As that air comes down the other side of the mountain, two things are going to be going on. First, that air has already lost a lot of moisture as it went up the mountain. It has very little moisture left in it by the time it gets to the far side of the mountain. And second, that air is descending. And as it descends, it warms up. And as it warms up, it has more ability to hold moisture. So that means there's nothing to push out any remaining moisture in the form of precipitation. And so we're going to get very dry conditions on the far side of the mountain. So anytime you have air flowing up over a mountain, the side of the mountain where the air goes up, the windward side, the side facing into the wind, is going to get a lot of precipitation. And the side where the air comes down, the leeward side facing out of the wind, is going to get very dry conditions. That dry area on the far side of the mountain is what's referred to as the rain shadow. The mountain is essentially creating a shadow where no rain is occurring on the far side of it. We can see a dramatic illustration of the rain shadow effect when we look at South America. Here we see a map showing precipitation levels throughout South America. And you may notice along the equator, we have the highest precipitation levels right in the middle of the Amazon rainforest. So that's due to that zone of low pressure that lives near the equator, moves a little north during the northern hemisphere summer, moves a little south during the southern hemisphere winter, but is always pretty close to the equator. And so we get very high levels of precipitation there. If we look, however, to the south of that, we see areas where we have a patch of very dry conditions right next to a patch of very wet conditions at the same latitude. those are areas on either side of the Andes Mountains. So that line represents the ridge line of the Andes Mountains, the top of the Andes peaks there. And what we see is that in the northern part of the countries of Argentina and Chile, we have dry conditions on the west side of the mountains, wet conditions on the east side. When we look at the southern portion of those two countries, we get wet conditions on the west side of the mountains, dry conditions on the east side. Well, that's because of the direction that the winds are moving in each of those two areas. The northern part of Argentina and Chile lies within those easterly winds that occur between 30 degrees south and the equator. And so the wind is blowing from the east to the west across the mountains. So we see precipitation on the eastern side and dry conditions on the western side. On the other hand, in southern Argentina and southern Chile, we're going to get winds flowing from west to east, prevailing westerly winds, which we already saw are going to occur between 30 south and 60 south. And so as those winds blow from the west to the east across the southern portion of the Andes Mountains, we're going to get wet conditions on the west side of the mountains and dry conditions on the east side. In both cases, we get precipitation on the side of the mountains that faces into the wind as the air is going up the mountains and cooling off. We get dry conditions on the side of the mountains that faces out of the wind, where that air is coming down the mountain and warming up.